Hello and welcome to A-Level Math with me, Almini Wilson. Let's make this a day for you to understand maths better. Decided, let's do it. My hair's up, so this means it's a serious topic. It is a serious topic. We need to really get into calculus today. This is the first section of calculus, derivatives. There's also a second part of calculus, which is integration, and together it's maybe the largest topic for the A-level syllabus. Something to keep in mind and to have close by while we're working. Definitely some stationery, quiet environment, I always say positive attitude, but also some physical things like love for you to have your smart calculator, the Casio FX911ZA Plus 2 or the older version. Please have your Cambridge formula sheet close by. There is a whole section on differentiation. Please don't let that put you off. We're not going to do all of it today. Just the basics, just for paper one. Okay, so we're doing derivatives. If you're still writing headings and dates, you're welcome to write today's date. We're doing calculus derivatives. And then I'm just going to dive into a question and explain to you why do we do derivatives. So let me show you. If you have a straight line, like y is equal to 3x plus 6, just want to test a little bit of your knowledge as we start. Do you know what the gradient is? Can you read off the gradient straight away? Is it a positive gradient? I hope that you can see that it's a positive gradient. So it's an increasing function, but I also want you to be able to identify that 3 is your gradient. So y is equal to mx plus c. This is your gradient. If I make it a little bit more difficult by maybe introducing a curve like y is equal to x squared, like a parabola, right? My question then becomes more difficult because now I'm like, what is your gradient? Where? I have to be specific because my gradient here is decreasing. It's a decreasing function, negative gradient. There it's stationary, so my gradient will be 0. And there my gradient will be increasing. So the problem I'm faced with when I have a curve is that it's ever changing. And that's also something, that's why I need my hands again. I want to explain to you that when you're dealing with a curve, even if it's like a trig function, the gradient is consistently changing. So what I need to explain to you is the two concepts of gradient. You get something called average gradient, where you have two coordinates and you sub it into a formula. But something that we're doing today will be instantaneous gradient. So what I want is, I just want to explain to you the two formulas. This is average gradient. And instantaneous gradient is going to be a process that starts with this formula. So for instance, if I tell you where my x equals 1. What's my gradient? You will be a little bit stuck because you're used to using two coordinates. Now, what you maybe got taught in your O-levels or in your IGCSE is when you substitute this in there, your x in there, at least you have a y coordinate then. So you've got an x, you've got a y, but you still need another coordinate. So what we try and do is we place another coordinate very, very close to that one. And that's where your first principle formula comes from. We place another coordinate extremely close to that one. If I want to just quickly remind you, the first principles that you might have done in your previous level was, I think your formula looks like this. H, but be careful, this would be where your limit as h tends to 0. But maybe I should just explain that to you. You want your x, the distance between x2 and x1, to almost be 0. But we can't have it be 0 because then the denominator is 0 and then it'd be undefined. So we try and make it as close to 0 as possible. And that's what today is all about, is trying to get to something that is very, very close to each other. If you do understand that, that is a different level. I have good news for you. I don't really see AS really asking you to do first principles. We've got so many other things to deal with. So in your AS or in your A-level phases, I just know about first principles, but I'm going to get you a shortcut today. The long way would obviously then be trying an X like 0,99999, sub it in, get your Y that's really, really close, and then do average gradient. But here's the good news. If you want to see it, let me just do it. 0,9999. You can forward this if this is not interesting to you. You can sub this in there and get a Y coordinate. I'm just going to type in 0,9999 squared to get my Y. And then I also get 0,9998. So when you type this into this formula, remember it's change in Y over change in X. Quickly type that in for me. It doesn't matter. You can choose this x2, x1, x2, x1. Just be consistent and then tell me what do you get when you're done there. Because I'm going to use that answer. Let me just type this in. You can type it in as a fraction if you like. And I'll show you what I'm busy with. I'm just going to give you the opportunity to also type it in. Okay, so it looks like this. Let me just make it clear so you can see what's going on. I just typed it in as a fraction. And I got an answer of 2. But please notice that if I'm here, it's going to be different. So this gradient here, it was 2. It does make sense that the gradient would be 2 because it looks like it's increasing. That gradient of 2 is then technically your average gradient, but it is the average gradient of something that's very, very close to that coordinate. If we then do instantaneous gradient, you can say that that is the gradient of the tangent that goes through that point. But now comes the shortcut, because I really don't want to do this more than once. I want to show you that if we take your curve and we do something to it, we do like a little formula, you can get the gradient anywhere on this curve without having to use average gradient. And the method looks as follows. If you derive your curve like this, I will show you how I got to that, but this is my notation for derivative, dy over dx. My method for derivative, look closely. You take your exponent times to the front, and then you subtract 1. That will also be on your formula sheet. If I can just quickly get my formula sheet close by. There we go. Check my notation, can either be f prime, or I can say dy dx. That is my rule. Look there, x to the power n, and then you times the exponent to the front and subtract 1. Remember, it's exactly the opposite. If we do integration, you would do the opposite. Add 1 to the top and divide. So what I've done now essentially is I've derived my curve. This is called my gradient function. And now I can move around anywhere on my curve. Even when x is 1, let's quickly check. If x is 1, what is my gradient? 2. Hey, we're matching with what we did earlier. What if my x was, now I can go back to my gradient formula. M is the same as dy dx. Very important to realize that. What if my x is 0? Right there. If my x is 0, hey, then I get a gradient of 0. And I want to just show you what that would look like. A gradient of 0 is horizontal. Think of cycling or jogging. It's no gradient, no slope. Whereas if you have a 90-degree, like perfectly vertical line, your gradient will be undefined. Undefined gradient, 0 gradient. Very important concept, that. So also, if you can make a little note, for turning points, your gradient needs to be 0. You can see that I can have multiple turning points. Let me just quickly show you. If you have a nice cubic function, this is obviously a gradient of 0. That's a gradient of 0. Wherever you're turning, please remember gradient 0, or dy dx equals to 0. We call them turning points or stationary values. I just wanted to show you again with this curve, how about if we're on the negative side, like let's say x is -1, sub it into the same formula, Do you guys see? I'm not changing. I'm just skipping around in like different notations, but my gradient function is 2x. What if my x is -1? I get an answer for a gradient then of -2, which makes sense. Please keep checking it on my sketch. If I had a coordinate there and I drew a tangent through it, then I have a gradient that's negative, and it would be -2. So the first thing to notice is when you derive a curve, you will get the gradient of that curve, and specifically the gradient of the tangent at a specific point. So that's the relationship between instantaneous gradient, which is derivative, and average gradient, which you're used to when you were doing lower levels of maths, if I can call it that. But to be very honest, we can't live in a land where it's only y is equal to x squared. We need to move out of that fantasy land and come into the real world where curves don't look like that. Curves look horrible. They could be brackets, square roots, fractions. So I'm just going to show you how to deal with that, because you can't really derive the way that I showed you now when you have those three scenarios. So let me show you what I mean. If you have a fraction, be careful. If you have a square root, be careful. And then also, like, maybe if you have a bracket and something to times it with, just be careful. So I'm making this as horrible as possible just to help you. You can't derive yet, so I'm just going to fix it. This is going to become x to the power -1. This is going to become x to the power half. I hope you know that. And when you distribute this x in, remember to do it with both your terms. And when timesing like bases, you add the exponent. So remember, there's a little imaginary 1. So here, I'm going to times them. I'm going to have x to the power -1 plus 1. So it's x to the power 0. And here I will have x to the power 3/2. All right. So then when I derive, this is the same as 1, right? So I can write here a 1, or you can write x to the power 0. When I derive, please make sure that you say dy dx to announce I'm deriving. Okay. So if you have this constant value, could have been a 1 or a 5 or a 7, whatever you have, you can still imagine that there's a 0 there, which means you times to the front. So this is going to fall away. Any constant will fall away when you derive. So it will still be in your original curve, but it's not going to feature here. Let me help you with the fraction now. What is the rule? Take your exponent, times it to the front, and then subtract 1 from your exponent. You can use the calculator if you don't enjoy fractions, but that's essentially what needs to happen. So then I can ask you, if this is the derivative, what is my gradient when x is equal to 2? Then you just sub a 2 in there and you get gradient. I can even go as far as to say, if this is my curve, what is the equation of the tangent when x is equal to 2? Then I just want to remind you, equation of a tangent, y is equal to mx plus c. It will always be a straight line. Doesn't matter what this curve looks like. I'm just going to draw a gibberish curve. If you have a straight line, that is your tangent. I will give you x. And with this x, you can sub it then into the derivative to get gradient. So then you already have 2 out of the 3. And then to find your y, you can sub it into the original. Very important that derivatives and curves are linked. If you derive the curve, then you'll get the gradient of the tangent. Golden words, what I'm saying now. Listen to that again. The derivative of the curve is the gradient of the tangent, always. Okay, let's dive into some more examples. The next example, I would love for us to do something a little bit more complicated, like a cubic. So when we do a cubic function, let me just write that down for you. You will have 2 turning points, which makes everything more interesting. So let's say we were dealing with something like this. A cubic meaning something like this is going to happen. It's going to have 2 turning points. And then I want you to imagine what can we call this turning point and what can we call that turning point. At that point, it's called a local maximum because I can't go higher. And at this point, it's called a local minimum because I can't go lower. And this is also called concave down, and that's called concave up. So all of that will relate to something that has more than one turning point. So let's quickly just derive this, because I want to make sure that you understand the rule. So when you derive, we say dy dx equals times to the front, subtract 1. Times to the front, subtract 1. You see that the x is then gone. And then constants fall away. So this is my derivative. How will I then find my turning points? Remember, your gradient, this is your gradient function, needs to be naught. So make it equal to naught. So then what I'll get to is, remember how to solve. I'm not going to teach you algebra today, but this is basically what needs to happen. So x squared equals 1. Very important when you square root to say plus minus. Yo, a lot of times when I'm marking papers, I almost want to cry if I see people not remembering to plus minus, because then you lose a mark or sometimes half your answers. So if we look at the two turning points, one will be a maximum and one will be a minimum. But which one's which? And how will I get my coordinates? I know my 1x is going to be 1 and my other x is going to be -1. But if they ask you for full coordinates, please go and sub this back into the original, because that will give you the y value. Okay, so if I sub this back, 1 minus 3 plus 1, what do you get? I get 1, right? -1, mustn't guess. So then the next one, if I sub a -1 in there, -1 stays -1, then this will become +3 plus 1. That's going to give me 3. So now that I've got my two turning points, or my stationary values, let me show you how to classify them, because I can tell you now, one has to be maximum, one has to be minimum. So how do I do that? I go into something called second derivative and check my notation. I've already derived. Now I'm going to derive again. So then the notation is going to be d squared y over dx squared. Let's just derive it again. So this second derivative is all about concavity. First derivative is gradient. Second derivative is concavity. Concave up, concave down. Okay, and the point where they actually change is the point of inflection. I like the explanation the other day. Someone said, if you're driving a race car, it's when you stop turning left and you start turning right. That is your point of inflection. But that's also, obviously, it's a concave down, concave up. When we have to classify something like a turning point, the easiest way would just be to look at concavity. So look at your second derivative. Substitute your 1 in. Don't set it equal to 0. Just sub. There's only space for the x, no space for the y. So then if I get an answer of 6, I know that you are concave up. So I can classify you as a minimum. Very confusing, because up sounds like maximum. So go draw it for yourself. So this is a minimum turning point. And then if I sub a -1 in, I get concave down. So that's then called a maximum. If they ask you to comment on the nature of your turning point or your stationary value, the nature, there's only one choice, or two choices, or one answer, either a minimum or a maximum. There's nothing else. Okay. It can be neither, but that is a little bit more advanced. I don't think that you will get this in paper 1 necessarily. So minimum or maximum, if it's equal to 0, obviously it's neither, but I feel like this is the part that you need to know well. Into a different type of question, but the same, I'm going to do the same sum, but I'm going to ask you, for which values of x is this curve increasing? Now remember, increasing, if you just think of like a rough sketch, this is not necessarily that sketch. This is increasing, right? Positive gradient. Then it's stationary, so 0. Then it's decreasing again, and then stationary, and then increasing again. So increasing, decreasing has to do with gradient. So when I'm increasing, I want my derivative. So this, let me just do it at the bottom here. I want my derivative to be positive. So if I ask you for which values of x is this increasing, you say bigger than 0. If you want to quickly just solve that, you can divide by 3, x squared minus 1. When I do inequalities, you're very welcome to just draw a straight line, plot your critical values, draw a little parabola going through it, and if they say bigger than, you color in bigger than. If they said, and then obviously the answer would be x smaller than -1, x bigger than 1. That is for increasing. Very important to notice, increasing has to do with gradient. The same with decreasing. I just want to show you what that sketch would look like. If I'm asking you for which values of x will the function be decreasing, I would get to actually exactly the same thing, except it would say x squared minus 1 smaller than 0, negative gradient. You'd have the same critical values, but then you'll color in here below the line. So then x must be bigger than -1, smaller than 1. One piece to color in, 2 pieces to color in. But the good news is you can use your calculator. If you've got a smart calculator, especially this new one, you can go to mode, go down, then go to inequalities, press the one that looks like a quadratic, not a cubic, because remember we are dealing with, I know we were dealing with a quadratic earlier, or cubic earlier, but now when you derived it, it becomes a quadratic. So I'm going to choose 1, and I'm going to choose one that has bigger than 0. So that's also still number 1. And then remember to type in A, B, and C. If B is 0, like in this case, I don't have an X, then you just type in 0. So type in 1 equals 0 equals -1 equals, and then look at my answers. X bigger than, x smaller than -1, x bigger than 1. I do prefer it though if you write it like this, and if you do have a method. Because remember, there are some method marks. If you just use your calculator, you know you're correct, but you might miss out on some nice method marks. I think that we've covered everything up to like increasing, decreasing. There was just one thing I forgot to mention when we were doing tangents. So I think if I can ask you for this equation, the same equation that we've been busy with, can we find the equation of the tangent? And then I'm going to explain to you what I mean with equation of the normal. So go back into this equation. I'm still dealing with x cubed minus 3x plus 1. If I ask you for the tangent, let's say where x equals 2, let's discuss that. So I'm asking you to find the equation of the tangent where x equals 2. And this is now the equation of the tangent to the curve. So if you wanted a y value, you're very welcome to sub this back into the original and see what you get. This is 8 minus 6 is 2 plus 1 is 3. So I've got a coordinate. That's already nice. If I have a coordinate 2 and 3, it's good, but it's not good enough because remember, again, I'm going to sketch my curve. If I've got a tangent going through there, it's going to be a straight line. At least I know the coordinate now, but I would love to know gradient as well. Please remember, gradient is derivative, and we've been dealing with derivative a few times today. That is my derivative of my curve. So if I sub my specific value in, I will get my gradient of my curve. So if I do this on 4 times 3 is 12, minus 3 is 9. So then I can write down, or like I said before, it is a straight line. Y is equal to mx plus c. I sub in my values as quickly as this. Y is 3, gradient was 9, x was 2. So I've got m, x, y, and then I work out my c. 2 times 9 is 18, bring it over, minus 18, so this becomes minus 15 is my c. So then y is equal to gradient 9. This is my final answer for tangent. But I said I forgot that we had to do normal as well. Look at my tangent there. Normal goes through the same coordinate. Very useful coordinate, this one. It's on the curve, it's on the tangent, and it's on the normal. The relationship between the tangent and the normal, they are perpendicular to each other. So if this was my tangent, remember derivative of curve is gradient of tangent. If you want the gradient of the normal, remember the sketch? Tangent, normal. If I just flip it around because they are perpendicular and change my sign, then I have the gradient of my normal. So then if I want the equation of my normal, I stick to this rule. I say sub in the same x, same y. So I'm going to sub in my same y and my same x, but check my gradient is going to be -1/9 plus c. And that's the only difference between tangent and normal. Tangent is like this, whatever, it follows the curve, and then the normal just cuts it perpendicularly. But they all share a coordinate. So please remember, sharing a coordinate, you can sub it into the curve or the gradient, the tangent, or the normal. They all share the same coordinate. Okay, I'm happy with that. Your formula sheet if you haven't already. I want you to focus on the bottom of this page. I have something called the chain rule, and I want to explain the chain rule to you so it can help us derive like difficult brackets, but also that chain rule helps us have multiple variables, like you have, let's say, x and y and time. Then the chain rule really helps. So let me just write it down from the formula sheet. You can join me. dy dx equals dy dt divided by dx over dt. That's the one from the formula sheet. I can give you other versions of this, but I just wanted to show you that it is true. I mean, if you flip this one around and you make it a times, it works. Another version that I've seen, dy dx equals dy du times du dx. This one also works. It's just not printed on the formula sheet. And what I want to use this one for is to derive a bracket, but not a nice bracket that we were doing earlier, a terrible bracket. Like for instance, if you have square root of like 3x squared minus 4x, that's terrible, right? So I want to help you by teaching you how to derive this the long way and the short way. So the long way is going to look like this. First, make this to the power of a half. I hope that you know that. Square root is to the power of a half. And then I want you to use something called u substitution. I'm going to make the problem child, this inside, I'm going to make that become u. So you can say let u equal this. And then when you go back to this equation, then obviously it's much easier to deal with. That's why we do u substitution. But you can't leave it there, because if my question was something like derive this, you're not even close to getting dy dx yet. Let me show you. Let's start by deriving this side. Check my notation. The top number says which equation, and the bottom number says which variable you are deriving. Remember the rule? Times to the front, subtract 1. Times to the front, subtract 1. Okay, then let's derive this one. Important, the notation. So dy du equals times to the front, subtract 1. Okay, so I've got that so far. Then I want to remind you of this formula that I wrote down. It still works out if you look at the bigger formula. If the du's cancel out, they are equivalent. So let me just write this down. dy over dx is equal to dy over du, which is this guy. If you want to, you can even bring back what your u was equal to. Remember we said we made u equal to that, minus a half, and then times by, the formula says, du dx. So 6x minus 4. And technically, you've successfully derived now a bracket. This is how we do it the long way, by using the chain rule. But I want to show you the shortcut chain rule. Now, the shortcut chain rule is lovely if you can remember how to do this. I'm going to do only one step. So just follow with me. You can go straight into the answer. Let me just focus, camera. You also need to focus at home. Okay, I'm going to derive straight away. Just trust me. dy over dx times, okay, we're going to derive the physical bracket. And then we're going to derive the inside. So separately, compartmentalize your brain. Times to the front, hey, I'm deriving my physical black bracket there. Times to the front, subtract 1. Times then by the derivative of the inside. Come on, that wasn't too bad. Then obviously you're welcome to times things with each other, but that is in essence the chain rule. The chain rule, we did it. We got to derive a bracket that was almost impossible to simplify. We can't simplify it to the power of a half. I really hope that you weren't thinking just times the half n. It doesn't work like that. So the chain rule is very useful in that case, but also for applications. The last thing we're going to do together for today will be applications in real life. And for that, we need a few word sums. I would love to use an example of maybe a leakage, like maybe there was, The Simpsons, he works at like a nuclear plant, maybe a nuclear leakage. What I want to say though is as soon as you hear there's a lot of writing and there's a lot of confusion, try and look for keywords like rate. If I hear rate, I think time. So the first thing I want to do with this scenario is let's imagine the patch of radioactive material starts with a radius of, let's say, 50 centimeters. Okay, so not a big problem yet, but it is increasing. This radius is increasing at a rate of 3 centimeters per hour. Now I can ask you something like, if this continues to happen, what is going to happen to the area? The area would also obviously increase. As you increase the radius, the area will also increase. And now my question would be the rate of area increase. So I hope I'm asking this right. You've got a circular patch of radioactiveness that's spreading. And it's spreading at this rate. Your radius is increasing at this rate. So let me write down a formula for you. We had it earlier. You could use dy over dx, dy over dt, divided by dx over dt. I'm using this one because now we've got radius, we've got time, we've got area. If you've got 3 different things that you're trying to relate, the chain rule really does help. Okay, so the chain rule helps, but I want to set up some formulas for you. If we're working with a circular patch, please look at this for a formula for area of a circle, pi r squared. Then if I ask you to find the rate of the area increase, obviously there needs to be some kind of dA dt, because I told you earlier, if you have rate, you want time. Also, some of my things that I gave you earlier, I told you the rate at which the radius was increasing was this. So that means my dr dt is equal to 3. So do you see, I've got so many different things happening here that I can try and relate that for you in another type of chain rule. Let's just change our variables a little bit. How about dA over dr equals dA over dt divided by dr over dt? It still works. Just check, it still works. If you flip this one, things will cancel out. And I have most of what I need, right? I've got dA. Oh, I haven't derived this yet, so I don't have a dA dr yet, but I can quickly get it for you. Look on the side. If I derive A, I'm going to call it dA over dr. So I'm going to derive this one. dA over dr is equal to times to the front, subtract 1, 2 pi r. And remember, I said that this radius when we started is 50. So dA dr I can use as 50. So then I have 100 pi for my dA dr. And then I just pop it into the formula. So I've got 100 pi, and then I've got for the ADT unknown. I don't know how my area is increasing when it comes to time, but I do know how my radius is increasing. So you sub in what you have, you leave blank what you don't have. If you just times that to the other side, you get 300 pi. So that means in real life that this area is increasing at 300 pi centimeters squared per hour. So that's how you use the chain rule in a real life scenario. Obviously, they can throw anything at you. Volume, surface area, even like 2D area, perimeter. Make sure though that you can deal with 3 variables in this formula. And just like that, that is the basics of derivatives. Remember, if you are in derivative form and you want to get back, you can integrate, but that's a whole different ball game. So please watch the video of integration and differentiation together, because they are each other's inverse operations. Thank you for joining me today. I would love to make videos every week and would love to hear your feedback. So please subscribe. See you again soon.